Hello, my name is Muhammad Azmi Idris. This is my final project. My project is related to deep learning implementation for iris recognition. So the problem statement for this case study, although biometric system has been used in several critical applications or systems, and if you notice that some countries already implemented the iris recognitions as part of the biometric system to enter the country. However, based on some research or several research, and in my project here, I rely heavily on this research by Ala Al-Awaisi and Rami Al-Qawaji and Stanley Ibsen, Shamos, and also Tariq. They have some very short paper regarding implementing deep learning for iris recognition, and one of those that they highlighted that there are critical limitations to this problem. These are critical limitations and problems regarding the existing biometric iris recognition system. One of them are noise in the sense trait and non-universality. Sorry about that. Intra-class variations, inter-class similarities, and vulnerability to spoof attacks, which is possible to happen. So, deep learning, one of the way of to find solutions to these challenges is to apply deep learning as an advanced subfield of machine learning techniques. And we are looking for high-level representations. And what I'm going to do here in the final project is to demonstrate the capability to predict the correct identity of individual based on his or her iris unique pattern using deep learning. So basically, because of this is computer vision or image recognitions, we are using CNN, and we also at the end use softmax classifier because these are multi-class classifications. And we just use the basic Python with Keras packages with TensorFlow. And I will explain later on about the database that we use for this project. Technology-wise, we use Anaconda installations with Jupyter Notebook. We have, it's not here, but we use TensorFlow as well as Keras. The data sets, okay, let me open this is the data sets that I use in my project. It's a bit challenging to get the data because of many of these iris data are available through institutions like universities where you need to apply for approval. I applied for the approval last week for several databases, several universities, but the quickest response that I received is from this university where they got this, they call it IIT Delhi Iris Database. And this data is actually hosted by the Hong Kong Polytechnic Universities. They have two folders actually. They have a normal folders and normalized images. The one that we use for our project is the normalized images. And this is the website that I used to download. The installation overview, we use Anaconda, we use Jupyter Notebook, and especially we use TensorFlow and Keras. Now, before we can move on with the model that we use, we need to talk about the data. The data that we use, again, this is based on the IIT Delhi Iris. It consists of 225 unique numbers or identification. Yeah, but each of the identification or each of the person that they take the iris picture consists of two sets of information. One is the normal images of the eyes, images, retina images. They have 10 of gray images, consists of 5 right eye and 5 left eyes. Total images we have 2240, and but for us to process this data, there will be a lot of noises. So there are several research papers about this, and I'm just focusing on one here, the same research paper that I showed to you just now. And two things that we need to do to this data: we need to process the data. Two things that we should do is to find ways to efficiently perform the localizations of the iris. And then another thing that we should do to localize and just focus on the iris regions. And another one that we should do, we should also normalize the images. So luckily, the same set of database provided a normalized version of the original images, which is very, very helpful in my project. So in my project, I'm not able to show how there are several websites that show how you can normalize, how you can localize and normalize these images, but I'm not doing it in my project. But what I did, because it's already have provided by the IIT Delhi Iris, is already provided with the normalized version, so I'm using the normalized version anyway. So these are the examples of the original images of eyes, and these are the normalized version of the eyes. You can see here that it's quite, it looks quite uniform. Whereas here you can see, you have eyelashes and have eye positions, and we'll see in my further presentation about the results based on these normalized images. So how we evaluate our model? We evaluate to see how, if we can solve this, if we can perform this prediction based on a shallow, a simple CNN. So we try our best, I try my best to come up with a simple CNN with the optimized as optimized as possible to achieve the highest accuracy. And we also want to see if the CNN and the convolutional network, if we increase the depth of this CNN, will it give us a better prediction? We also look at the pre-trained model like VGG16. For this project, I only evaluate one pre-trained model, which is VGG16. So before we do anything, we set up our environment. And let me show to you my, not this one, okay. So these are the, this is in the attachment of the submission of the project. This is all my work. We have for the pre-train, you do it separately. Yep. So let us proceed with this one. So we set up the environment, so all the normal requirements, all the requirement common packages that we use, and we use most of them are from Keras. And we need to distribute. Now each individual has 5 normalized iris images. Now we're not using the normal images, we just use the normalized images. So instead of having 10 for each 224 individuals, we only have 5. So it's a very small set of data. That's a bit challenging. So what I did, we only have 2 sets of data. We have train and validations. I'm not able to provide data for tests because it's just, this data set is just too small. The way we evaluate this model is not by applying the model to the test sets of data. I think it's just enough to look at the accuracy based on the Keras history results once we feed the model. Okay. So our focus is just going to be on the validation accuracy of the model. So before that, so what I did, we have 5 normalized iris for each individual. So I group all of the individuals instead of having for each images for each individuals, I regroup them into 5 groups, where all individuals will have their image in their iris here in all of the folders. So what I did is a very simple. I need to get 80% of training data and 20% of validation data. So I push this is not 1 to 5, sorry, this is 1 to 4. So we have 5 groups. Sorry, this one. So we have 1 to 4, group 1, 2, 3, 4 under training data, and iris into group 5 will be the validation data. So total we have 80% and 20%. Here, based on the code, I just put 20% for the test, but I'm not using it in any of the fittings or any of the models to fit the models. And I just ignore it for testing purposes, only for my debug purposes. Before we can move on, we need to hard encoded our labels, because these labels are numbers. These numbers are more on like descriptions. So we just hard encoded. So you can see here this might be 200 1000 plus records. So you can see this is one hard encoded applied to the data. As we know, the images come under different shapes. Originally it comes from 432 plus 48. This is the normalized version of the images. So somehow I just come up with 200 and plus 1 times 150. So we need to reshape all the data to the correct shape for the models. Again, ignore the test images. We're not using this one because of this contain the same data from train and validate. You don't want to do some. We don't want to come up with inaccurate results. So we just focus on train and validate. So as I said before, we try to optimize the simple CNN. Here first we develop our first CNN, a very simple one, not that deep. So we have convolutional, we have dropout, and interestingly we have max splitting and flatten. This is where you do the dense. We also have 2 dropouts, and we fit the model that we have here. We have dropout because of the regularizations. We don't want to model to overfit. And this is the basic setup that we have. And then remember, one of the evaluation criteria that we're looking for is to see whether depot CNN can contribute for better performance, prediction performance. So we have one. This is just a simple one, additional convolutional, and we have CNN2. This one is also deepest. This is the deepest that we have. Now, if we look at here, we apply 2 dropouts for the very single. So we are evaluating the simple CNN. So we can see here form is a little bit strange because we have a higher accuracy for validations. Normally we see validations lower than the training, but based on my reading, I noticed that we have 2 dropouts, and this dropout might the dropout will give lesser features to the training data, the training process, and while in testing, this is incorrect. This is testing. Sorry, this is testing. Okay. While in testing, all features is used and scaled appropriately, and then it will make the test time, the validation value much more robust and better accuracy. And yeah, we need to do something with the dropouts. And another reason why these validations are higher than training, because the data is not been split enough. Because we have very small data, I've not decided to do for random. I just need to make sure that everything is there. And this is true. I have very limited data, and it's my decision is, to have each identification, each individuals to exist in both train and test. Yeah. So the only thing that we can do here is just to play around with the dropouts, which I did. So looking at this is such a big difference. So I think it's capable. I think it is acceptable. Actually, we need to find out to reduce the gap between train and validations. So what we did, we originally we have dropout of 0.2, 0.5. We take out one of the dropout. We just leave only one dropout at the end of the model. The dropout is still relevant because we will try to avoid overfitting. Now we run all of the models, and we have 4 models altogether. And we have the simple model, and we also have deeper models. So you can see here that when we train the models is trained in GPU machines in Amazon AWS E2. I don't have GPU machines. It takes a very long time to run, and the only possible way for me is to run to the Amazon AWS E2. So these are the results that we have. One thing that we also look at is the duration of time to process these epochs. However, I decided not to put the time because when I test all of this model, there's no significant differences between this deeper network. As you can see here that this is the including training and validations. Let's look at the next slides. Here we have 4 models. You can see that the shallow it makes sense that the simple CNN converge faster. Less than 2 or 3 epochs is already getting the highest accuracy. However, we have 4. Of course, we have a deeper network, and we have to take longer epochs to process. However, we anticipate that we're going to have better accuracy for deeper network. It doesn't look like that, although you can see here is higher than the rest, but you can see that validation depth 2 also quite high. Based on if you look in general, you can see that validation deep 2 have the highest accuracy, but so it's not a very big difference. So I think that for us to have an optimized model, because all of them have a range 96 to 98, I think it's best to have a very simple model. It runs quickly, and it's also at the end the same with the rest of the CNN, and it performs not better but quite the same with the rest of the deeper CNN. Perhaps I can try to get more. I should have twice or thrice deeper, but for simplicity's sake, I just choose to have this kind of setup. So the last thing that we're going to do, we want to compare with the VGG16 that we import from Keras. So these are the architecture of the VGG16. And what I did, we combined this with our own layers to do the multi-class classification. We use softmax, and we set up we just train this part, but we don't train the original VGG16 because it's already been trained. So VGG16 is combined with dense layer. VGG16 model switch off. We used 100 epochs for the training, not 50, because of the depth of VGG16. I believe that it takes more time to converge. And here we can see that for 100 epochs, you can see that the accuracy is a little bit lower. It's so much lower than the custom CNN that we have developed. So perhaps if we put the time longer. Perhaps we will get a better result, but um, a simple way we can see that, if you look at the simple CNN, can achieve quickly, perform better, um, less than 3 epochs, which is better compared to BGG16. Oops, sorry. Um, that's it from me. And as a conclusion, to answer, if we go back here, we can see that we are able to have to predict for 96 and 98. Now, what are the challenges that I think we have here? I think that we need more data. If we have more data, we can do more randomness in our data, so that we can try to have a normal kind of results where we have trainings higher than the validations. But I read through, this is pretty normal. And the conclusion here that yes, it is possible to do deep learning for iris recognitions. The iris recognitions, as I mentioned before, the best way is to process the images through localization and normalizations, so that we can remove all of the noises, and then based on the normalized images, even a shallow network able to perform better compared to a deeper network. So that's it from me. Thank you for listening, and bye bye.